In the last video, we defined pressure as force per unit area. Now let's look at a device that is used to measure air pressure. It's called a barometer. And you take a long test tube or a long closed glass tube, and you fill it up with mercury, and you place it upside down in a dish of mercury. So this is all mercury in here. Now you see something funny happen. The mercury pulls away from the side of the tube, from the top of the tube. Even though this was all filled up with mercury, when you tip it over into the dish like this, it'll pull away. And you'll see a small amount of space here. And in there, you have pretty much a vacuum. Now, the height of the mercury tube, the mercury column, we'll call H. And it's a measure of how much atmospheric pressure you have. Now, what's going on here? Why does this column stay up here? Why doesn't the whole thing spill out when you turn it upside down? It's because the atmosphere is exerting pressure on the dish. And that is pushing, that is squirting the liquid up the tube. It only squirts up so high, though, only to a column of that height. And you really have two pressures that are being balanced here. You have a pressure from the mass of fluid, and you have a pressure from the atmosphere. Now, we could take this device, this barometer, and use it to measure the atmospheric pressure in pascals if we wanted to. If only we could work the height of the fluid column in there, we could just have a ruler next to this thing and read off the ruler something that we could turn into or use as a pressure of the atmosphere. So let's work on working the height into this expression right here. Now we said that pressure was the weight of the fluid column on this side. So it's going to be the mass of the fluid column, I should say pressure from the weight. And the weight is going to be the mass of the fluid column times the acceleration due to gravity that we talked about last time, divided by the area of this thing. So that's going to be equal to the pressure from the atmosphere. Let's just call this pressure P. So we're turning it into an equation here, but this is very inconvenient because I'd have to drain all this liquid out and find out what its weight was, and I also would have to know the cross-sectional area of this. There's a little, if this was a circular tube, I'd need to know the area of that circle there. That would be the area that I put here. And I don't want to be doing that. But there is something easier that I can do. If I want to figure out the area, I can use a relationship that involves the volume. If I have any kind of a shape, say I have a footprint or something, and it has an area of A. And let's say it has even thickness. So the thickness is even. Let's call that H. It's just like our H up here. The volume of anything, any shape, no matter what shape it is the area times the thickness. As long as it has the same thickness everywhere, this formula will work. It's a pretty simple formula. So if I look at my area here, I can replace it. The area is the, what? The volume over the thickness. So let's replace the area in our formula with that. I have at this point mg over the volume divided by the thickness, which is h. So here's my equation at this point. Alright, that's still kind of a mess. Let's get the h out of the denominator by multiplying the top and the bottom of this fraction by h, the height of the fluid column. I still have to know the volume of the fluid, and I have to know the mass of the fluid. But do you notice something about what I have right here? If I have mass divided by volume, what is that? We saw way back in the first chapter that that's something called density. Let's call that D, density. M over V is the density. So I could write dGH equals P. And this is very convenient. I'm going to put a box around this. This relates the atmospheric pressure to the height of the fluid column that I have right here. And it will also let me calculate the pressure exerted by a column of fluid in other problems. For example, suppose I've got the ocean surface here. And I get a diver down here. Swimming. That's a terrible diver. But suppose the diver is at a depth of h. And let's suppose that on top of the ocean I have a pressure of, let's say, 100,000 pascals, which is pretty close to what atmospheric pressure is. The pressure on the diver is going to be equal to the atmospheric pressure plus the pressure of the fluid column that is here. So, the pressure on the fluid column is going to be density times acceleration due to gravity times height. I would need to know the density of the ocean water here to do this calculation. The density of the ocean water is typically 1.025 kilograms. Well, if I'm going to use kilograms, it's 1,025 kilograms per cubic meter. The acceleration due to gravity is about 9.8 meters per second. And I have to know the depth that the diver is at. Let's say the diver is swimming at a depth of 10 meters. I can multiply 1025, let me make this clear, 1025 times 9.8 times 10 and get this. Now, since I'm using all SI units here, I'm going to get out pascals for that second term. So I can just take 1025 times 9.8 times 10 in pascals plus 100,000, and that'll give me the pressure that is being exerted on the diver.